Here's my thoughts, my plans here. Um, I'd like to finish up like the content for chapter 8 here this semester. I don't think I don't want to try to cram a quiz down your throats here on Friday. That feels like you probably have enough going on. Um, or even worse, a test, right? Like pass. Um, so what we'll do is we'll do the chapter 8 content here this semester, and then when we get back, we'll do like quiz and test on chapter 8, which is not great, but it's better than trying to cram it in now, I think. Deal? Yeah, all right. So let's pick up where we had left off in chapter 8. So we've been talking about probability. So last time we talked about kind of counting, right? We talked about events and outcomes and that kind of stuff. We're going to continue kind of talking about probability. So just kind of review some basic facts or rules about probability. So the probability of any event is going to be some number between 0 and 1, i.e. some percentage between 0 and 100. Can't have negative probability. Can't have probability greater than 1. Okay. All possible outcomes together, those probabilities have to equal exactly 1. So if you add up all the possible outcomes, you better get 100% of the possibilities there. Again, when we say 1, you could think of that as 100% also, right? If all outcomes of a sample space are equally likely, like if you're rolling a single dice or drawing a single card from a deck, the probability that event occurs can be found using the formula. Number of outcomes corresponding to that event divided by the total number of outcomes in the sample space. So it's basically just like a percentage, right? Part out of whole. And then the probability that an event does not occur is 1 minus the probability that the event does occur. That's like a complement property is what we would call that. Okay, so in summary, if we want to write this more mathematically, for any event A, P of A is between 0 and 1. If S is the sample space, probability of the sample space should be 1. The sample space, again, contains all possible outcomes. In the case of equally likely outcomes, the probability is the number of outcomes divided by the total number of outcomes. And then the last one we call the complement rule. The probability of not A, so that little apostrophe next to the A is one of the notations for not A for the complement, is equal to 1 minus the probability that it does occur. So when we talk about probability, there's really kind of two different types of probability. You have experimental probability and a theoretical probability. So if I flip a coin 10 times, the probability that I get, or if I flip a coin once, the probability I get heads is 50%. Now, if I actually flip that coin one time, I'm either going to get heads or I'm going to get tails, right? So like theoretical, experimental. right? If I flip a coin 100 times, how many times do you expect me to get heads? 50, right? If I actually flip the coin 100 times and we counted, maybe I'll get 57 heads, right? Could happen. Now, what you'll find is that the bigger your experiment, the closer that experimental probability should be converging to the theoretical probability, right? If I got 57 heads after I flipped it 100 times, if I flipped the coin 1,000 times, and then 10,000 times, and 100,000 times, and 1,000,000 times, eventually we'd expect that amount of heads to be basically at 50%, right? So for the most part, what we'll be doing is calculating theoretical probabilities. That's the probability of an idealized situation that results, and the results that should occur based on our given information. So again, just the probability of A is the number of possible outcomes divided by the number of outcomes in the sample space. Experimental, that's if we actually set up an experiment, we do trials, like we flip a coin, right? So the probability, our experimental probability of flipping a coin might be, if we flipped it 100 times and we got 57 heads, would be 57%. Right? Everybody's okay there? Okay. Oops. All right, let's look at an example, and we're going to try to decide which one is which. A baseball player has a batting average of .250, meaning that he has safely hit a ball and reached base 1 out of every 4 times he steps to the plate. In a particular game, he has gone to the plate 3 times and not reached base. Your friend argues that the baseball player will absolutely safely hit the ball and reach base at the next at-bat. Give 2 reasons why your friend might be wrong, or why your friend is wrong.
Just because it's 1 out of 4 chance doesn't mean it's going to get it on the 4th. It's 1 in 4 chance.
Right. So let's try to use the words theoretical and experimental probability with kind of what you're reasoning, but I think you have the right idea. His batting average is a
Theoretical?
Nope. Experimental, because he actually has gone and hit the ball, right?
Yeah.
Those are recorded. They happened in the past. How is the friend trying to use that experimental probability as a theoretical, right? That's kind of mixing the two in a way that you probably should not do. The other good reason you could give is just like when you're at the casino and you see like red come up on the roulette wheel like 10 times in a row and you're like, I'm gonna bet everything on black. These are independent events, right? The probability of you hitting a ball does not depend on what you did the previous at-bats, right? It's still a 1 in 4 chance. Everybody's okay with that idea? And let's say it's mostly independent, I guess maybe if you're like in a groove or something, but like, you know, like players getting hot is something that's really hard to measure, and there's not a lot of statistical evidence that actually exists outside of like normal variances in probability. All right. What we want to talk about next are mutually exclusive events. When we say a mutually exclusive event, that means that two events are disjoint, or there's nothing in the intersection of them. So an example of mutually exclusive events might be flipping a coin and getting heads, and rolling a dice and getting 6. There's nothing in common between flipping a coin and rolling a dice. There's no outcome in common. An example that's not mutually exclusive might be drawing a card that's red and then drawing a jack from a deck of cards, because there are cards that are both red and jacks. Everybody's okay with that? So we say two events A and B are mutually exclusive. Also, we could use the term disjoint. Those will tend to be used interchangeably. If they have no outcomes in common, and so they can never occur together, that is, their intersection is empty. So the probability of A and B occurring is 0, because there's nothing that can happen at the same time. If two events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. So if I have the probability of A or B, that's just going to be the probability of A plus the probability of B. So for example, if I asked, was the odds of rolling one die and getting a 3 or a 5, are those mutually exclusive? Can you get both of them happening at the same time? Nope. So the probability should be 1 out of 6 plus 1 out of 6. Everybody's okay with that? Let's look at a numeric example that's a little bit more complicated than some of our simple dice and card examples we've been using so far. When people create codes for their cell phones, the first digit follows the probability model shown in the table below. So we have 0.009 is the probability that your first number is a 0, 0.3 that it's a 1, 0.174 that it's a 2, etc., etc., etc. Quick aside, why do you think the first number is so often a 1? The first number on the keypad, maybe, sure. We're playing psychologist now. This has nothing to do with math.
It does keep going down.
Here's what I would think.
On the number line for the probability, right?
Here's what I would think. 4 digits. What kind of number is often 4 digits? It starts with a 1. A birth year? Like lots and lots of people's birth years. I know yours don't, but lots and lots of people's birth years start with a 1. I think that's probably tipping, the choice there. Especially the older folks that have a hard time remembering stuff. Plus the ever popular 1, 2, 3, 4 password. Anyways, let's continue on. So find the probability of the event that the first digit is 1. So all we have to do is go to the probability table. What's the probability the first digit is 1? 30% or 0.3. Everybody's okay there? How about that the first digit is more than 5? So what outcomes are more than 5?
6, 7, 8, 9.
6, 7, 8, and 9. Are those outcomes mutually exclusive?
Yes.
Yes, because the first digit can't be both a 6 and a 7. That's impossible. There's only one number that can go there. So we can just add up the probabilities then, right? Everybody's okay with that? And so if we do that, we get 0.221 or 22.1% if you prefer. Again, there's no preference given to whether you give it as a decimal or a percentage. Although if it's a percentage, you best have the percentage symbol after it. And if it's a decimal, you best not put a percentage symbol after it. But either answer is okay. Feel good so far? How about the probability the first digit is odd? What are the odd digits here? Someone other than Diego, maybe. Okay, I'm going to call on Megan. Good. You were making faces like you knew the answer, but you just didn't want to raise your hand, so I appreciate you knowing immediately what to do and then not volunteering. And again, none of it, we can't have two digits at the same time, right? This is, by definition, all these things are going to be mutually exclusive. So we can just add up the probabilities, and we get 0.603. So far, so good? Okay. The probability that the first digit is either 1 or greater than 5. So again, those outcomes would be mutually exclusive, but specifically they would be 1, 6, 7, 8, 9. Since they're mutually exclusive, we can just add up the probabilities, or we can take our work from the previous two questions and just add them together to get 0.521. You guys okay with that? Okay. Find the probability that the first digit is not 1. Okay, good. So we know the probability that we're 1 is 0.3. So we're going to use that complementary rule. So 1 minus 0.3 should be 0.7 or 70%. Or on the alternative, you could add up the probabilities for 0, 2, 3, 4, 5, 6, 7, 8, 9. But yuck, right? Use the complement if you can. It's often makes life quite a bit simpler. So far, so good? Okay. Find the probability the first digit is an odd number or a number larger than 5. Are these mutually exclusive? No, right? What is in the intersection between the odd numbers and the numbers larger than 5?
7 and 9.
7 and 9. So we can add them up individually, like we did before. Or alternatively, you could take this and then subtract off the two probabilities that you're counting twice in doing so, right? Because the probability of B counts 7 and 9. The probability of C also counts 7 and 9. We don't want to count them twice. So you could take these two, add them up, and then subtract off the 7 and 9, which have been counted twice, and you'd get the same answer. Ooh, hold on.
So you're just not counting it twice.
Correct. You do not count it twice. Yeah, whatever you do, whether you count it twice and then subtract it off, or you recount everything just one time, do one or the other, but don't count them twice. So when we do that, we get 0.721 if we count them individually, or the other way we count that is taking the probability of B and C and then subtracting off the probabilities of 7 and 9, because those would be counted twice when we did the probability of B and C. And we get the same answer. And again, when I say why you subtract the overlap over once, I think we covered it, right? You guys get it? There's that. That was not so bad. Let's do some of the problemos there, huh? Oops. All right, should we call on random people? I like that idea too. Sounds like fun, doesn't it? Where's my thing? That's what I'm looking for. Here, let's let everybody see. Random student, 5th hour, fresh roster. Give me a random student. Oh, of course. Do it again. Lexi, you're up first. Below is a probability model for students who took the 2013 AP Stats exam. Prove the model is a legitimate probability model. That's one thing that you would need to do, yep. So if you add those all up, they do equal 1. And the other thing you have to have is all the probabilities need to be between 0 and 1, which they clearly are. But that's it. That was pretty tough. Everybody got it? Who's next? Zach. Zach. Find the probability that a chosen student score is at most 2. I mean, if you need to do some arithmetic, but you could just tell us what we're adding together and then trust that we're... Okay, what does at most 2 mean? So the score is at most 2. What scores are at most 2? Great. At most means less than or equal to. So if we want the probability that the score is at most 2, we'd add up the probabilities for 1 and 2. And whatever that comes out to, 0.2 or 0.423. Right? No big deal. So far, so good. Let's see who's next. Christian. Find the probability that a chosen student score is at least 3.
So it's just 3, 4, and 5. Probability of 3, 4, and 5.
Great.
It's like 5 something.
577. Or what else could have you done?
You take 1 minus probability that it's at most 2.
Yes, very good. You could have also done it as 1 minus your answer for part B. That would also work. Either is correct. In this case, there's not a lot of advantage by doing the complement because it's pretty, there's just not a lot of data in here, but there's like 40 things in your table that might seem more appealing to do 1 minus your previous answer. All right. Next example. There are 30 students in a stats class. After taking a poll, the teacher discovers that 20 play an instrument, 18 take art, and 12 do both. Construct a Venn diagram for the situation, and that's going to fall on Elise.
How do you want me to construct a Venn diagram? Just like go in it?
Yeah, just tell me what it's going to look like. So we have like the 2 circles, right?
And then on one side,
And I'm going to call this one the instrument and this one the art. So there's my universal. Okay.
so 18 in the art. Like 18 students,
So you want to put 18 here. Okay.
and then 20 students in the instrument.
Okay.
12 in the center.
Okay. So if I add those up, I get way more than 30 though. So I don't think that's quite right. Because even now, if I look at it, if I look at the art circle, how many students are in the art circle? 30. How many should be in the art circle? 18.
So you do it in the center and the art one.
Well, the center says there's 12 that do both, right? So 12 definitely take art
Okay, so
and play an instrument. How many take just art and don't play an instrument?
18.
18 total students take art. That means the ones that play instruments and the ones that do not.
Wait, I'm sorry, what are you asking?
So the 18 students that take art are students that play instruments, or they might not play instruments. All we know is that they take art.
Okay.
We know that 12 students taking art also play an instrument, right? How many students take art but do not play an instrument? There you go. Now let's do the same thing for the instrument. Good. How many students have we placed? Okay. How many students should there be in there? 30. Where do the other 4 have to go? Not in the center.
Or on the 2?
On the 2.
Like on the instrument art?
Nope. They go in neither, right? Those are the 4 kids that don't do either of those 2 things. Is that okay? Again, there's no penalty for wrong answers or having to talk it through or whatever. I don't need to, I'm not trying to embarrass anybody. We're just trying to, learn how to do some stuff, right? Refresh our memories. We had done this a little bit last time, but it's been some days. Gavin, you're up next. You're being asked how many students take art but do not play an instrument. You mumbled 6 is correct. So you're just looking at things that are in the art circle but not in the instrument circle. All right. And if I wanted a probability there instead of how many students, what's the probability that a randomly selected student takes art but does not play an instrument?
6 out of 30.
Excellent. 6 out of 30, whatever that decimal is, or whatever I think you can probably mean 0.2. Probably 0.2. Right? 6 out of 30 is 1/5.
Yeah.
Yeah. Okay. Did you not say? I maybe mumbled and I didn't understand
I
it.
think it's 1.
Oh, yeah, that's okay. All right, let's see. Aiden, you're next. So example 3 says, what is the relationship between educational achievement and home ownership? A random sample of 500 U.S. adults was selected. Each member of the sample was identified as a high school graduate or not, and a homeowner or not. The two-way table displays the data. Use the symbols to define all possible outcomes for the data above using high school graduates G and homeowners H. So what does G mean? Yep. Okay. So that's like this column here, right? And then what are we going to call this one? Great. So what symbol should I use? Yeah, the apostrophe is our symbol for the complement. And then we should do this one. Homeowner is going to be and then not homeowner should be, yeah. Everybody okay with the notation that we use there? Just as an aside, sometimes different textbooks will use this for a complement, or they'll do this for a complement. Those all kind of mean the same thing. You can use those all interchangeably. I think our textbook uses the apostrophe, but if you're looking at other resources, or they may use other notations. All right. Next up is Matthew. Suppose you choose a member of this sample at random. Find the probability that the member you choose is a high school graduate. Well, how many high school graduates are there? Okay, I agree. How many total people are there? Great. So the probability should be? What percent of them are high school graduates? $310 out of 500, right? That's it. They'll do. Could you reduce that fraction? Sure. If you want to make it a decimal, is that okay? Sure. If you want to write that decimal as a percentage, is that okay? Sure. But that answer that we wrote down there is fine. So far, so good? Luke's not here. Diego. Probability that you are a high school graduate and a homeowner.
40 out of 500.
Nope.
Oh no, yeah. It would be 221.
There you go. Everybody okay there with that one? Cool. Who's next? Isaac. High school graduate or homeowner? It's not 340 because 119 of those are not high school graduates. Oh, so yeah, we have to be a little bit careful, right? So you want to say this is tempting, right? But that's not quite true because these are not mutually exclusive. So you'd have to do that. So you have 340 plus, graduate is 310 plus 340 minus 221 is how I would do that. Or I think this comes out to be the same as that, right? But I'm going to write it out as like, this probability plus this probability minus that probability, because I think it's a little bit easier to kind of go back and see rather than just like 310 plus 119. That was a hard one because you had to realize they were not mutually exclusive. Aiden, back to you, it looks like. Using the two-way table above, construct a Venn diagram that contains high school graduates and homeowners. So we'll draw that. Zoom out so we can see the table at the same time. So where's the 310 going then? Here? Nope. Because that whole circle needs contain only 310. I'll give you a hint. When we're doing this, you always want to start with the intersection. So how many are both graduates and homeowners? There you go. So let's start there. Now, of the 310 graduates, how many are left? 89, which coincidentally is that, right? Graduate and not homeowner. What do you think is going to be over in the rest of H then? Not 71. It's going to be the 119, right? The homeowner, because that's not homeowners down here. That's going to be out here. So 119 should be not graduates, but still homeowners, right? So you're still in the H circle, but not any part of the G circle. Does that feel okay? Again, it's not difficult to do, but it takes practice, right? You have to do a couple and then before you're like, okay, I got it. So that's that. What do you guys think on this? It's all right? I'm going to go erase all this stuff that we wrote down in case you wanted to go back and look at it. I always dump the keys in at the end. think I broke my computer. Come on, computer, do some stuff. All right. So in chapter 8, again, continuing on with probability to section 3, title here is operations with events. So again, we have our basic rules of probability that we looked at last time. This is the same four basic rules that we saw in 8.2. What we're going to talk about next is what's called expected value or expectation. We can find an expected value much like the expected counts that we did for the chi-squared test. The expected value is the value that we'd expect to get a certain event based upon a given distribution of events. So if, again, we're flipping a fair coin 100 times, how many heads would you expect?
50.
50, that's the expected value. If you rolled one die 100 times, or let's say 60 times, how many times would a 5 show up? 10. So it's just the probability of it times the number of trials. That's all we're looking at here. Is that okay with everybody? Okay. Oh, I stole my own thunder. How many tails would you expect if you flipped the coin 25 times? I mean, it's 12 and a half, guys, right? Does that make sense? No, but it doesn't have to. Expected values don't have to make real world sense. It's much in the way like if you're talking about like game theory in baseball, like an out is worth, like some decimal percentage of a run, right? Like, or a hit is worth like 0.23 runs. Like it's the same idea. Like, that makes no sense. You can't have not a whole run, but it's the same idea. Like you're you're calculating an expected value and how much this is worth. All right. Again, mutually exclusive events means that there's nothing in their intersection. So if I do the probability, I can just do the probability of one plus the probability of the other. Everybody remembers this. We just did it like literally 10 minutes ago. So like we just did in some examples, if we give you a two-way table here, so this is looking at students that are their gender and they have their ear piercings. So if I define the events A being is male and event B has pierced ears. What is it doing here? Okay, so we do that. Probability we have pierced ears is the probability of B. So I just take the 103 out of 178. Is male and has pierced ears. So that's the 19 out of 178. Is male or has pierced ears. Here we have to be careful, right? Because it's not mutually exclusive. So I'm going to do the probability that I'm male plus the probability I have pierced ears and then subtract off the intersection. Or I can just add the 3 together. Is that okay with everybody? Either way of thinking about it is fine. It's fine. So if we construct a Venn diagram from this, again, you want to start with the inside, the intersection, and then the male that don't have pierced ears is the stuff in A, but it's not in B, so that's the 71. The stuff in B that's not in A is the 84. And the stuff that's in neither circle is the no on both, or the complement on both. That's the 4. Everybody's good? So in symbols, the intersection is A and B. The part here, the 71, is A and not B. The 84 is not A and B. And the 4 is not A and not B. Is everybody okay with that? All right. So again, for non-mutually exclusive events, we've mentioned this a couple of times. But in general, the probability of A or B is the probability of A plus the probability of B minus the intersection of the two. What if they're mutually exclusive then? Well, this probability would just be 0, and you'd end up with the mutually exclusive formula we discussed last time, right? If they're mutually exclusive, the intersection is empty, so there's no events there, has a 0 probability. Okay? So here are 2 main formulas, mutually exclusive, and then 2 events in general. Honestly, folks, this is the one that everything becomes this, and if it's mutually exclusive, I just fill in a 0. All right, let's talk about, hi.
Hi, I'm sorry to interrupt.
That's okay.
I was down here.
No problem. Oh yeah, sure. Let's talk about independence. So when knowledge that one event has happened does not change the likelihood that another event will happen, we say the 2 events are independent. So for example, if I say the probability of rolling or flipping a coin getting heads, and then flipping the coin again and getting heads again, it's like 2 heads in a row. Those are independent events, right? Whatever happened when I flipped the coin the first time doesn't affect what's going to happen when I flip the coin the second time. It doesn't change the probabilities at all. Now let's say that I am drawing cards from a deck. Let's say I take out a card, and then I take out a second card without putting the first card back. By removing the first card, I've changed the probability of getting the second card, because now the second choice is only out of 51 instead of 52. That's an example of a non-independent event. Everybody's okay with that? Or if I'm pulling names out of a hat, like the first name that I pull out changes the probability when I pull the next name, because there's fewer names in the hat now, right? Everybody's okay? 2 events, A and B, are independent if the occurrence of one does not change the probability that the other will happen. So, in this case, for independent events, the probability of A and B, of getting heads and then heads again, is just the probability of A times the probability of B. So the probability of flipping heads 2 times in a row is 1/2 times 1/2, or 1/4. Everybody's okay with that? Flipping a coin and getting heads 8 times in a row is 1 out of 256. This is why people are willing to give you $1 million if you pick a perfect NCAA bracket, because you have 64 choices, or 64 or 32 choices in the first. Oh, there's 64 games in the first round, right? 32 games. Okay, so 32 to the 30, or 1/2 to the 32, and the next round is now not independent. Those are dependent, because it depends on if you got the first round correct or not. So that probability of getting this on random is just astronomical small. So the insurance company feels pretty good about selling you a policy to cover your $1 million if somebody actually does it. All right. The best way to determine if two events are independent is to find the probability of both events occurring at the same time and compare that to the product of the events occurring individually. So that's a way to test for independence. So this goes back to kind of that card example I gave you before. So when looking at a string of multiple events, we need to know if the events are independent from one another. Then we need to know or need to determine whether we are going to use replacement. The probability without replacement means that subsequent events are changed by what happens first, like when we talked about drawing cards from a deck or pulling names from a hat. Probability with replacement means the subsequent event will not be affected by what happens first. So if I'm pulling names from a hat, I read the name and I put it back in there, mix them back up, and I draw again. That second draw's probability was the same as the first draw's probability because everything was still in the hat when I did the second draw. Everybody's okay with that? Okay. For instance, you have 5 green gummy bears, 4 red gummy bears. You pick out 1 green gummy bear. The probability that the second gummy bear will also be green, if I do this without replacement, should be should be 4 out of 8, because there'd be 4 green gummy bears left and 8 gummy bears left in my pile, right? If I do it with replacement, it should be 5 out of 9, right? Because there's now 5 green gummy bears, because the one I picked out first I put back. And then there's 9 total gummy bears still. Okay. Did I not have an answer in there? That's weird. Okay, whatever. So mutually exclusive events are not necessarily related to independent events. You can have, oh my goodness, I almost knocked that over. I did this yesterday and ruined a whole bunch of stack of papers. I have somebody's test here that's got all soda stains at the bottom of it. I'm pretty embarrassed about. So let's look at an example. Let's suppose a coin is flipped twice. That's both mutually exclusive and independent, right? It's mutually exclusive because you can't get you can get heads or you can get tails, but you can't get both at the same time. And it's independent because if I flip the first coin, the second coin flip has no bearing from the first coin flip, right? Everybody's okay with that? In a deck of cards, if you pick 2 cards and examine their suits, so the suits would be like hearts, spades, diamonds, or clubs, that's mutually exclusive because there's no 2 cards that have 2 suits on them. But it's not independent because pulling the first card changes the total number of cards left in the deck. Because now you're drawing out of 51 cards. Everybody's okay with that? In a deck of cards, if I pick 1 card, replace it back in the deck, and then pick the second card, if I'm looking at Jack or Diamond, or Jack and Diamonds, that's not mutually exclusive because there are Jacks that are also Diamonds, so there's some intersection there. But it is independent because I'm putting the card back after I draw it. Is everybody okay? That you can have all of these all these possibilities. All right, so let's look at an example here. Blood types for people can be one of 4, O, A, B, or AB. The distribution of random blood types for randomly chosen people in the United States, China, and Russia are given below. What is the probability of AB, or of type AB in the United States? And what is the probability of type B in Russia? How would I figure this out for the United States? What should the probabilities add to? 1. So I can just take 1 minus 0.43 minus 0.41 minus 0.12. Similarly, can I do the same thing in Russia? Yes, right? So each row is a separate sample space. So for the US, 0.04. And for Russia, 0.18. Everybody's good? Okay. Dirk lives in the US and has blood type B. Type B can only receive from types O and B. What is the probability that a randomly chosen US citizen can donate blood to Dirk? So we look in the USA row, and we look at the probabilities of O or B, and those are mutually exclusive because you can't have blood type that's both O and B at the same time. So we just add the two probabilities together. Now I did this with the general rule because I always think about the general rule and just put a 0 there if they're mutually exclusive. Okay. What is the probability of a randomly chosen person from the US with blood type O and a person from China with blood type O? So what is the probability of randomly choosing a person from the US with blood type O and then a person from China with blood type O? Step 1. How many events are occurring? 2. There's picking the person from the US and then picking the person from China, correct? Is picking a person from the US with blood type O, is that mutually exclusive? Yeah, right? That's only one way that can happen. Similarly in China, correct? Are these independent events? Is choosing the person from the US going to affect the probability of choosing the person from China? No. So this is going to be, the probability of A and B is going to be the probability of A times the probability of B, or 0.43 times 0.36. So about a 15% chance of being able to do this. Everybody okay? Oh my goodness. What is the probability of choosing 3 people? 1 from the US, 1 from China, and then 1 from Russia, all of which have type O blood. We do the same thing, right? So 0.43 times 0.36 times 0.39. It doesn't matter how many independent events you link together. You just multiply all the probabilities individually, right? That's the takeaway from that problem. What is the probability of randomly choosing 3 people, 1 from each country, all with the same blood type? So how many different ways could that occur? 4 ways, right? You could pick 3 people with O, 3 people with A, 3 people with B, and 3 people with AB. Correct? And those are mutually exclusive, correct? So probability of 3 O's plus the probability of 3 A's plus the probability of 3 B's plus the probability of 3 AB's. And do the calculation for the probability of 3 O's. Those are independent. So it's O in USA times O in China times O in Russia. And then the same thing with AB and AB. So there's our 4. Each of those are independent. So about a 10% chance that if you choose randomly someone from these 3 countries, they'll have the same blood type. Is everybody okay with what we did there?
So you multiply the probability for each country.
For each type
Each type.
across 3 countries.
Just
So,
added those up.
and then I added those up.
Okay.
Yep. Another example. It is estimated that 17% of all computers bought from one manufacturer require 1 repair job during the first month. That 7% will need repairs twice in the first month, and 4% will require 3 or more repairs. What is the probability that a computer will need no repairs? Well, let's be a little bit careful about this. Let's use some symbols and kind of like notate this, because oftentimes it's a little bit easier once we've symbolized this. So event A is 1 repair, event B is 2 repairs, event C is 3 or more repairs. So I know the probabilities were given to me for event A is 17%, event B is 7%, and event C is 4%. So I'm going to record that up here at the top. So a computer with no repairs, that's mutually exclusive of these 3 events, right? You can't have no repairs if you also have 1 repair, 2 repair, 3 or more repairs. So what I know is then that's going to be the entire sample space, right? No repairs, 1 repair, 2 repair, 3 or more is all the possibilities. So that should equal 1. So no repairs should be 1 minus those 3 probabilities, or 72%. Is everybody okay there? What is the probability a computer will need no more than 1 repair? So that could be 1 repair or 0 repairs, right? So it should be P of A plus no repairs, so 89%. What is the probability that a computer will need some repair? Well, that's 1, 2, and then 3 or more, so it's 17 plus 7 plus 4, or 28%. Or you could have done this with the complement rule, right? You've done 1 minus no repairs. It's the same thing as getting some repair. If you bought 2 computers from the manufacturer, what is the probability that neither will require repair? So that's going to be an independent event, right? The purchase of the first computer has no effect on the purchase of the second computer, whether they needed repairs or not. So it should be 0.72 times 0.72. So about a 52% chance. That's not great. It's a pretty bad computer company. If you bought 2 computers from the manufacturer, what is the probability that both will require repair? So that's going to be the probability of some repair and then the probability of some repair, correct? So some repairs was 1 minus no repairs. Everybody's okay with that? Or you could have used the number, whatever that was, 0.28. Or you could have added, which is what we got by adding these 3 together, right? So a little less than 8%. So next we want to talk about something called a conditional probability. The probability we assign to an event can change if we know that some other event has occurred. So for example, if we're talking about like picking your teams for the NCAA bracket, picking round 2 is a conditional probability because if the team that you picked to win in round 2 lost already in round 1, that probability of them winning goes to 0, right? Because they're no longer in the tournament. So when trying to find the probability that one event will happen under the condition that some other event is already known to have occurred, we're trying to determine a conditional probability. The probability that one event happens given that another event is already above. Okay, so we said it twice. Suppose we know that event A has happened, then the probability that event B happens, given that event A has happened, we denote by the probability of B given A. So A is the thing that's happened. B is the thing we want to find the probability of, provided that A has already occurred. So let's talk about flipping a coin. Yeah? Okay. Say let's find the probability of flipping a coin and getting 8 heads in a row, given that we already have gotten 7 heads in a row. What's that conditional probability? So the probability of getting 8 heads in a row, given that we've already gotten 7 heads in a row.
Doesn't change.
It's just 1/2, right? Everybody's okay with that? It's just a simple example. Okay. So let's figure out a formula that we can use to find the conditional probability. So the probability, or our formula we're going to use is the probability of A and B divided by B. So again, if we go back to my coin flipping example, the probability that we get 1 coin heads after 7 heads would be 1 over 256. Divided by the probability we get 7 heads in a row, which is 1 over 128, which simplifies down to 1/2 that we kind of knew intuitively. Notice that if we flip the conditional probability B given A, the numerator does not change, right? A and B is the same as B and A, but the denominator does. Everybody's okay? Okay. So let's look at an example here. So we have a two-way table. E represents the grade comes from an EPS score. That's engineering and physical science. And L is the event the grade is lower than a B. So if I want the probability of L,
Add up all the
add up all the things, okay? So I should have 3656 out of 10,000, right? Find the probability that the grade comes from an EPS score, given that the grade is lower than a B. So I'm going to be looking at the EPS scores, and then of those EPS scores, I'm going to look at the ones lower than a B, and I'm going to divide that by the total grades that are lower than a B. So basically, I'm looking at what percentage of the grades that are lower than a B come from EPS scores. Everybody's okay with that? What if we flip it? Lower than a B given EPS scores.
divide by 6.
Yeah, good. So far, so good? Where are we at here? Let's stop here. We still have like 30 slides left to go in this section. And we just got to a new topic, which feels like a good time to just stop. So Friday, we're going to try to finish 8.3. And then our days next week, we'll spend kind of working on our Chapter 8 homeworks. I'm not going to have a OneNote problem set check for the last of this Chapter 8 homework. You're just going to show it to me in class at some point, rather than like worrying about loading into a notebook or into your OneNote or whatever. So if you do it on OneNote, that's fine. You can just show me your OneNote, not a big deal. But at some point during the week, next week, I'd like you to show me like the 8.1, 8.2, and 8.3 homeworks. Deal?
Is there a rubric for the final video?
You know what? I don't think I want to do that. Let's just not. Right? It's one less thing. It doesn't accomplish anything. What I've heard is that you actually don't have to be here on the exam day, and I don't actually have to do anything, so I'm getting like conflicting information. So that was the most recent communication I have, is that you're not required to be here if we don't have anything, like the final exam is completed. I'm required to be here, but you are not. So it's fine. I'll have grading to do anyways. I have 13 papers to read and try to grade. You know? 13 is a low number for this course. But I haven't had to try to do it as a final, have it done like for a final exam grade. Usually it's due in the set. Typically we make it due in like, I don't remember when the due date was. I think it was one of those where it's like it's due at the start of second semester or something, and then I can just sit on it, grade like one a week for the next 2 months or something, and grind it out slowly. But I don't think I want to make a video. I think it was just something to do because I thought I had to have something to do on the exam day, but now I've been told I don't. So that's one less thing for you guys.
Yeah, thank you.
Which feels like
Thank you.
nobody needs anything more to do, right?
Yeah.
Yeah, okay. So yeah, I'm gonna